All right, so yesterday, 5.1 talked about working with continuous variables. All chapter 5 talks about is basically, and the reason we only talk about one section is we want to draw the line between what discrete variables meant and what continuous variables meant, okay? And then that allows us to, if we understand the difference between those two, it allows us to understand maybe the difference and why, in this case, we're going to address probabilities by areas instead of through the use of those formulas that we were doing with discrete probabilities, okay? Yesterday we talked about taking, we can take any function. So when we talk about continuous distributions, this curve here, this red curve is referred to as a probability density function, okay? Not a big deal whether you remember that or not, in my opinion, but it can be uniform, okay? It could be exponential, and in this case we have one that is like a bell curve, okay? And this is symmetric, okay? So if we have a symmetric probability density function, they are a family of functions, much like any other function we've ever talked about, like x squared. There's a family of parabolas, right? You can move them left, right, up, down, you can reflect them, all that kind of stuff. Same thing happens with these things. We can move them left and right. So if I make mu -1, it can move to the left. If I make it -2, moves to the left, okay? And ultimately, that is because, if you remember anything from like Algebra 2 or college algebra, when we have a function like this, and I'll go to it's actually on your paper here. Remember, whenever we subtract something from x and run it through a function, and before we run it through the function, that is a horizontal shift, right? That's moving it left and right, okay? Whenever we multiply by a number out front, okay, and in this case, we're going to be multiplying by essentially 1 over sigma, okay? When I multiply by that, that is a vertical stretch, okay? And we can see by changing mu, we can move this thing left and right. If I want to move it to the right, kind of do that, okay? And if I want to change the height of it, okay, maybe I change it to 0.6. I can change it to, anything I want. Make it 2, okay, make it 0.1, gets real tall, okay? But there's a family of curves. So what we're basically arguing here is if I take away, just so it doesn't confuse us, take away the x-axis here real quick. Let's see here. Just take away the numbers on the x-axis. If I take those away, each one of these, as I change my sigma and change my mu, okay, that might represent, let's say that we're talking about, let's say if I taught stats for 7 periods throughout the day, and we had a test, and I take and I fit that test in a distribution, and I find out that for all 7 classes, it's a normal distribution. One class might have a distribution that sets up like this, okay? Depending on what the mean and the standard deviation is for that class. So let's say first period looks like that. Second period might have a mean, so let's say that this test was like out of 5 points. That would be kind of maybe weird, but let's say that second period, they had a mean of 1.75, and they had a standard deviation of 0.5. You can see that graph would be different than first periods, right? And we do the same thing for third period, fourth period, fifth period, sixth period, and seventh period. We would have 7 different types of distributions. They'd all be symmetric, but they'd all be kind of moved around left and right. And talking about their vertical stretch, they'd all be a little bit different than one another, okay? And if I wanted to then use those curves to like maybe ask the question, what if I pull somebody out of second period? And what's the probability that their score is, they scored maybe at least a 3 on that 5-point test, okay? Well, if I had to do that and I did it with every single one of these family of curves, I would actually have to have quite a bit of knowledge about calculus to be able to do that, because each curve is a little bit different, and to find these areas under these curves then would be a little bit different every single time. Does that make sense? But if I can take something and I can, like one of those classes, and say, I'm not going to deal with the scores out of 5, but what I'm going to do is I'm going to say, I'm going to fit all of these scores. So whenever I find the mean of like this class, I'm going to take that mean. Let's say that mean is 2.5. I'm going to take that mean of 2.5 and I'm going to reposition it. I'm going to say, nope, the mean is now 0. But now everything else is going to move the same way. Does that make sense? So individual scores are going to also move. The mean moved from 2.5 down to 0. So all my other scores, the individual scores, are also going to move as well. Does that make sense? Okay. And what happens, we also like to get the standard deviation. Instead of standard deviation being like 0.5 or 0.7 or 2 or something like that, we want the standard deviation to be 1. Okay. And now what we find out is that this is what we refer to as the normal standard curve. Okay. Basically, what that allows us to do now is say, if I look between -1 and +1 as my interval, okay, for probability, do you see the empirical rules probability of 68% here, right? Okay, so I'm able to now take all 7 classes and individually take every one of those classes and morph its distribution down to this. And now, because of the calculus that we understand with this, I can apply that calculus to all of those other individual statistics classes. Okay, and it's standard. We call it standardizing. Okay, so now if I want to know, what is a score? What's the probability somebody had a score of 3? Well, I would have to go through. Well, I'll show you the formula that allows us to do this. I would have to transform that 3 into a score for this curve. Okay, and then maybe it falls between -1 and +1 standard deviations, and then I can say, well, that's a 68% chance or something like that. Okay, but because we know the calculus with this curve, it eliminates us having to know, and being able to standardize things, eliminates us having to know anything maybe about well, where'd that one go? Oh, not -58. Okay, it eliminates me having to know anything about that curve. Does that make sense? Okay, and the calculus involved defining the areas underneath that. So, that's what this is going to be addressing here, okay? The most important of all distributions is the standard normal distribution, okay? It's bell-shaped. It's used in all disciplines, okay? And here's just a few, okay? But pretty much you name the discipline, there is some aspect of using the normal distribution to allow people to make decisions, okay? So we got psychology, business, economics, education, sciences, nursing, medical field, it's huge. Even if you go into being my wife is a speech therapist, and she has to do this. She goes into nursing homes with like stroke patients, and she'll have to give them an assessment. She'll basically ask them a bunch of questions, ask them to do some things, and she evaluates those tasks and then figures out where does this person fall on the normal curve based off of people in the same type of situation. So people that are maybe in their 80s or something like that. Does that kind of make sense? And if they fall in the normal range, then she cannot give them treatment because the insurance company isn't going to say that that was necessary treatment. But if they fall outside of an acceptable standard deviation, then she can give them treatment, and the insurance company says that based on your assessment, it was justified. Does that kind of make sense? So all your professions are going to, at some level, use standard deviation, the mean with the standard normal distribution. It says the normal distribution has two numerical descriptive measures, the mean and the standard deviation. Those are two things that decide what the curve looks like, okay? And if we go through this formula here, you don't need to memorize this. I just wanted you guys to see that it is a function. Algebra 2, college algebra, does this thing pass the vertical line test? If I look at this right here, does it pass the vertical line test? Yeah. Absolutely, okay? So this curve is a function. We call it the probability density function. Now, obviously you don't need to memorize that, but that's where that curve comes from, okay? Evaluate some x values, get the y values back, plot them, and that's the curve that shows up. It says if x is a quantity to be measured that has a normal distribution with mean mu and standard deviation sigma, we designate that by writing this, okay? That's how we kind of define the continuous variable. I don't prefer this format, okay? But I'm not going to use it very often. But if you ever see that, what they're saying is that your continuous variable is normal. That's what the n stands for. And the first number is your mean, and the second number is your standard deviation. So for like the normal standard distribution, your mean is 0, and your standard deviation is 1. Okay, so that's how I would write that for the normal standard distribution. Okay, yes?
What does the shoulder mean? Does it matter?
Doesn't matter. Don't worry about it right now. Now, if we look at our curve, okay, there's some features here that we need to understand. The curve is symmetric about the vertical line that passes through the mean. Okay? So when we go back to this here where standard deviation is 1, mean is 0, change my axes here. Oh, 1, not 11. Okay, so this segment right here, or this line right here, that is the mean, that is the axis of symmetry, okay? And it is also the median, okay? And you see on the paper it says, in theory, the mean is the same as the median. We're not talking about this yet, but we'll eventually talk about, well, how do I know whether the data that I have, the raw data that I have, fits whether a normal distribution or not, okay? The idea is that there's really no situation where something is perfectly normal or perfectly symmetric, okay? But they are very, very, very close. And if they're not perfectly symmetric, you remember, if they're not symmetric, then they got to be skewed one way or the other, right? Okay? So if they're not perfectly symmetric, that means they may have to be skewed to the right or skewed to the left. And in those skews, left or right, the median and the mean deviated from one another. They were different, okay? But if it's nearly symmetric, almost 100 or 99.99999999999% symmetric, then the median and the mean are, one is just a hair to the side of the other one. Does that kind of make sense? So that's why it says in theory, we're going to say that the same, but in actual practice, they might be just a hair off, okay? But it's not a big deal. It says the normal distribution depends only on the mean and the standard deviation. If we kind of decipher this formula, okay, obviously 1's a real number, 2 is a real number, pi is a real number, e is a real number, okay? If you guys remember working with like Avogadro's number in chemistry or something like that, you used e. The natural number is what we refer to it as, or Napier's constant. Sigma is a real number, 1/2 is one real number, x is our variable, mu is going to be a real number. And mu, though, that's going to be that's a variable value. And so is sigma. So those are the only two things that are going to dictate what our curve looks like. Okay? We like to make, like I said, we like to make mu 0 and sigma 1. Okay? And that gives us a pretty nice curve. So the normal distribution curve becomes fatter or skinnier depending on sigma. So going back to college algebra again, this is the scalar multiplier, 1 over a essentially. So you can either stretch it or shrink the height of your distribution. And then think about, I think we already talked x minus mu. Okay, that's moving it left and right. If it's minus, it'll move it right. If it's plus, it'll move it left. But the above two bullets indicate there are an infinite number of normal distributions. Okay? We don't want to learn about every one of those because that would be impossible, right? Okay, and it would involve quite a bit of calculus if we wanted to even address a handful of them. So what we do is we learn about one, the one that has a standard deviation of 1 and a mean of 0, and then we conform all others down to it. Okay, and we'll talk about how we do that, but it's called standardizing. So we'll come up with what we call a standard normal distribution. Okay. In order to standardize something, we need a tool to do that. The tool that we're going to use is the z-score. You guys remember talking about z-scores back in chapter 1 or 2? Okay. Comes back here. Okay. It says the standard normal distribution is a normal distribution of standardized values called z-scores. Okay. A z-score is measured in units of the standard deviation. So if we were to take your guys' test scores, okay, and we put them, we say it's a normal distribution, then every spot on that curve represents a test score, okay? Once I take your test scores and I standardize them, now on that distribution, they're called z-scores. They're no longer referred to as our test scores. Does that make sense? Okay. But if I ask, well, what's the probability that somebody got less than a 45 on that test? Well, 45 would be the test score, but I need to now standardize that and get a z-score that matches to the 45. And that's kind of what we're going to try to address and learn how to do here. So the standard normal distribution with a mean 0, standard deviation 1. And to standardize anything, we have to use this formula, okay? Your z-score is going to equal x minus mu divided by the standard deviation, okay? That z-score tells you how many standard deviations the value x is above or below the mean, okay? Positive z-scores are above the mean, negative z-scores are below the mean, okay? It says all distributions that are normal have different heights and thicknesses due to their standard deviations and means. But each one can be converted to a distribution that has a mean of 0 and a standard deviation of 1. That is the critical component, the critical understanding that we need to know for what we're going to do and what drives the rest of this course. Okay, I'm very fearful that I'm gonna show you how to do things, and you're gonna be able to successfully get these values, but not know what we're really doing. Does that kind of make sense? We can be calculators. Does your calculator really know what you're trying to do with it when you're typing stuff into it? It just calculates, right? You guys can do that. You'll be able to be successful with this. But your calculator doesn't know that you were trying to find maybe the vertex of something, or doesn't know that you're trying to find the zeros of something, okay? I need you guys to have that understanding of what we're really doing here, okay? So I'll try to, some of the things that we go through, some of the activities that we go through is going to try to convince us of that paragraph there, okay? So once this is completed, we can easily analyze individual data points and use the new distribution to determine probabilities easier, okay? So it's called standardizing, hence where we get the word standard normal curve. Okay, so this is a demonstration. This hopefully will explain this with an example. Okay, so suppose that we gathered data from last year's final chemistry exam and found that followed a normal distribution with a mean of 60 and standard deviation of 10. Okay, so we could do this for anything, no matter what you're collecting data on. Measuring people's heights, measuring lengths of phone calls, measuring distance that you travel to work, or that your peers travel to work, whatever, okay? If you find that it follows a normal distribution, you can do what we're about to do, okay? But if I'm measuring, and even if we're measuring the same thing, if I'm going back to those 7 classes, and let's say 7 classes of chemistry here, each one of their distributions is going to be a little bit different. One class might have a mean that is 70, so their distribution might look something like that. Does that make sense? Another class might have a mean that was 50. So their distribution might look like that. One might have a mean that was 80, but their standard deviation was like maybe, I don't know, like 1. So you might see something kind of like that. So every class is going to have something a little bit different, right? I want to take every one of those curves and make it into this curve. Okay, so that's what this is all about. So this particular class, they had a mean of 60. Okay, so the mean is right there. That's mu. Okay. Come on, there we go. So that's my mean. This distance right here is 1 standard deviation. Okay. This is 2 standard deviations. This is 3 standard deviations. Okay. So if I asked you in this situation, if I know that this is the mean, and I know that the standard deviation is 10, and I asked you the question, what is the probability that a particular person pulled out of that test scored less than a 49%? Okay. In order to do that, first thing we would have to construct this probability density function that is appropriate with this mu and this sigma. Okay. And then we would have to, and I don't think my GeoGebra is going to do this very easily. We can try this. So mean was 60. Mu is 10. Or sorry, sigma is 10. So that is going to move this thing. Let's see what my axes are. There, and let me adjust the standard view back out to 60. Yeah, I don't think it's gonna, when I'm going back to, I apologize for this, but like right there, okay, there is, so it is bell shaped, but it's very gradual. Okay, it almost looks linear here. That obviously, reading this bell curve would be very difficult, right? Okay, but what we'd be asking is, okay, if I come down here to 49, okay, and now shade underneath that red curve and above the x-axis and to the left of 49, how big would that area be in comparison to all of the area underneath the curve? And that would be my probability. Okay, that's a nasty task to address with this specific curve. Okay, so what we do is we say, okay, I don't like that mean being 60. We're going to convert that down to a mean of 0. And if we run through this formula, this is kind of where this formula comes from. If I take my x value, that's these data values down here. These are the values that the discrete or the continuous variable could take on. And I put 60 there, minus 60 divided by 10. Does that give me 0? So that takes this mean of 60 and it converts it down to a mean of 0. Now everything else is going to move the same way. Okay? So if I go to 70, go 70 minus 60 divided by 10, does that give me 1? That make sense? So then that 70 is going to convert down to being that 1. 80, so I'll have 80 minus 60 is 20. 20 divided by 10 is 2, right? And then the 90 is going to match up to 3. 50, so now I have 50 minus 60, so now I got a negative 10 divided by 10, so that's going to give me my negative 1. 40 is going to match up to negative 2, and 30 is going to match up to negative 3. Does that make sense? Now, it does not matter. It does not matter what your mean is. So if we had another class that had maybe a mean of 70 and a standard deviation of 5, that formula is still going to take their mean and convert it down to 0. And it's going to take that standard deviation of 5, so the next value would be like 75, and it'll convert 75 down to 1. Does that make sense? So it takes every single score over here and converts it down to, ultimately for us, we're going to be basically looking between -4 up into 4 all the time. Okay? But this is called standardizing. Okay? Now, if that's the case, so negative, or not negative, but a score of 49 would represent that area right there. Okay? Well, 49 is not over here. 49 is no longer a value because we standardize things, right? So that specific score of 49 also needs to be run through here, and I need to find a z-score. So if I put 49 in here, I get 49 minus 60 gives me negative 11, divided by 10 gives me negative 1.1, right? So now I find negative 1.1, and the way I've got this shaded should actually be more like this, okay? So now if I can find that area, that will tell me the probability that somebody scored less than a 49. But I standardize that 49 to negative 1.1. Does that make sense? Okay, so let's kind of talk about this. Let's see if we can recognize this on this here. So if we got a standard deviation of 1 when it was normal and a mean of 0, and we'll go back to standard view just to make it look a little bit better. All right, so that is our curve, right? Okay. So right now we had a z-score. A z-score that we were interested in was negative 1.1, right? Okay. So we were looking for the probability that the z-score was less than negative 1.1. Okay. If we're going to do it that way, we need to basically put a vertical line at negative 1.1 underneath our curve. So that's going to be this b value, and I'll show you other calculators that make this a little bit easier. GeoGebra actually has something built into it that is this. But that would be kind of that value at negative 1.1. Does that make sense? That line right there, and it's kind of hard to see. But we want the probability that we would be less than, it said less than 49%, right? Which for a z-score is less than negative 1.1. So I want to shade everything to the left of here, right? So this term here, this a, actually needs to be, I'm just going to make it negative 100, so it shades everything in there. Does that make sense? Okay. Now if I ask, what is that area? That area is the definite integral. Okay, remember talking about breaking that up into a bunch of rectangles, right? Okay, well, the definite integral does that, and it gives me that number right there. 13.57% is everything between or below negative 1.1. So the probability that somebody on this test scored less than a 49% is 13.5. There's a 13.5% chance that I randomly choose one of these tests, pull it out, and it was less than 49%. Does that kind of make sense? Okay. Hopefully the symmetry here makes sense to you. If I go from an a value, just the coding here, I've got this set at negative, so I put negative 100, but I've got it set up to where the slider that this is referencing only goes to negative 30, which is fine. It really only needs to go to like negative 5. But if I go up to a b value of 0, so I shade in half of my bell curve, do you see that you're getting half the area, right? Okay. But that's the idea of being able to take any curve, okay, any normal distribution, and standardize it so that we can answer questions about particular situations easier. Does that make sense? Okay. What's nice about that then is if we're doing this for all my classes, Now, standardizing allows us to compare somebody from first period to somebody from seventh period. Does that make sense? Okay. It allows maybe somebody that's judging ACT scores or SAT scores at a university to compare your score with somebody else's score that comes from maybe a different country or maybe even different state or whatever. Does that make sense to everybody? Okay. We'll stop there. Okay. I have opened up some, if you have access to Math Excel, I've opened up some assignments. They're going to be open until January 14th. The rumor is that we're going to have computers back by early to mid next week. So once we get those back, then I'll leave the assignments open that we've encountered since all this has happened. But once we get the computers back, then we'll go back to our normal routine of homework and giving you 2 days to complete it, that kind of stuff.
So will those assignments become like mandatory?
No,
I
no.
think